So today we're just going to review some of the basic integration techniques that you learned in Calculus 1. So first of all, let's look at the indefinite integral. Now if you recall, the indefinite integral is essentially the antiderivative of the function. All right, so if f of x is some function where it happens to be the derivative of this capital F of x, okay, so this looks a little weird because we got lowercase and uppercase f's, but essentially the lowercase f is a derivative of capital F. And when we integrate the lowercase f of x with respect to x, we end up with the antiderivative, right? We're essentially asking what is f of x the derivative of. So let me write that down. So what is f of x, lowercase f of x, the derivative of, right? So what function did it come from? If we took the derivative, so we should always be able to take the derivative of the antiderivative and get the function that we integrated back. So for example, let's take this integral of 2x dx. Okay, we're asking what function has a derivative of 2x. All right, and so we have to kind of go in reverse. This is the power rule, and if you recall, x squared has a derivative of 2x. So x squared is an antiderivative of 2x. But that's not the only function that would have a derivative of 2x. 2x plus 4 would also have a derivative of 2x, or 2x minus 16 would have a derivative of 2x. And really, any 2x plus any constant would have the derivative of 2x. Okay? So we always have this plus c. With indefinite integrals, when you're calculating antiderivatives, you always have this plus c, because when we integrate any constant, we get 0. So we really get a family of functions. Now, these antiderivatives or indefinite integrals of common functions all come from the basic derivative rules that you already know. So like, for example, you know the power rule. And essentially then the integral of x to the n is using the power rule in reverse. The same with integral of a constant, k. You can kind of think of it as being kx to the 0, right? So you're using the power rule in reverse there too. You know that the derivative of natural log is 1 over x, so it would make sense that the integral of 1 over x is natural log, right? We're just doing things in reverse. Now that one in particular is a little bit weird, because it's actually the natural log. When we integrate 1 over x, we get the natural log of the absolute value of x. So, and that just has to do with the fact that the domain of 1 over x and the domain of natural log are different. We can integrate 1 over x for negative values, but the natural log is only defined for positive values. So when we integrate 1 over x, we have the natural log of the absolute value of x, plus a constant. All right, so the rest of those I think are fairly straightforward. You can probably see how they come straight from the rules for differentiation, for taking derivatives, okay? And if you ever want to check your integral, take the derivative of your answer, and you should get the function that you integrated, right? So for example, if I take the derivative of 1 over k cosine of k x, then I should get the positive sine of kx. Okay, so that's always a way that you can check your integrals too. Just differentiate your answer and check to see if it matches what you integrated. Okay, and then we have some properties for the sum and difference of integrals and the constant multiple of an integral. All right, so let's get down to business and do some integrals here. All right, so here we have integral of the square root of x plus cosine of x. All right, now I'm going to rewrite that just so that I can use, if I write x the square root of x is x to the 1/2, then I can use that reverse power rule. And then, you can leave this as cosine of x dx. Okay? And then I'm going to end up with, so I'm going to take x to the n plus 1, so 1 plus 1/2 is 3/2, over n plus 1, right? And n plus 1 again is just 3/2. And then the integral of cosine is the sine of x. And then I have to add plus c. Now, when you have this reciprocal of 3/2, you end up with 2/3. So sometimes I skip the step where I put the 3/2 in the denominator, and I just take the reciprocal. So essentially, it's the reciprocal of n plus 1. So sometimes I skip this step. But you could also write this solution as 2/3 x to the 3/2 plus sine of x plus c. All right, let's try another one. Here, we have 5e to the 0.1t minus 1 over x. Now, remember, we have a difference of two functions. Now we have the sum of two functions here. Sometimes, you can just leave it that way. But I could break it up into two different integrals. But I know that the integral of a difference is the difference of the integrals. So I'm just going to skip that step. So when I end up here, I have the 5, and that's just going to hang out in front. And then when I integrate e to the 0.1t, I end up with 1 over 0.1 e to the 0.1t. And then I have minus the integral of 1 over x, which is the natural log of x. And then I have to add plus c. And I can clean this up a little bit because 5 over 1/10 is going to be 50 e to the 0.1t minus natural log of the absolute value of x plus c. All right, so those, I kind of think of the basic Calc 1 integrals in 3 different categories. There's recognition, where you're just recognizing the form of the integrand, where you recognize, okay, it's the power rule, or if it's cosine, or if it's e to some power, and you recognize the antiderivative. And so that's the first time, is just the first type of integration technique that you learned in Calc 1. The second type is an algebraic rewrite, where initially it doesn't quite look like something that you would know how to integrate, but if you rewrite it algebraically, you can make it into something that looks like it's more manageable, more doable. And then the third type that you learn in Calc 1 is the basic substitution. So in the next example, I'm going to go through a couple of integrals where we're going to use, we're going to do an algebraic rewrite.